National Electrical Safety Code, or NESC, generally does not mandate the use of an equipment grounding conductor, or EGC, with a notable exception for coal mines. The primary focus of the NESC is ensuring the safety and reliability of electric power systems. The rationale behind not universally requiring an EGC stems from the code's perspective that an EGC is not always crucial for the safe functioning of an electrical system. To understand this better, let's delve into the purpose of an equipment grounding conductor and the context in which the NESC operates. An equipment grounding conductor provides a low impedance path for fault current to return to the source. This path facilitates the quick operation of overcurrent protective devices such as circuit breakers or fuses in the event of a ground fault. By rapidly clearing the fault, the EGC minimizes the duration of dangerous touch potentials, thereby reducing the risk of electric shock. In many electrical systems, particularly those governed by the National Electrical Code, or NEC, the EGC plays a vital role in personnel safety. However, the NESC addresses a different scope of electrical systems. The NESC primarily covers electric supply and communication lines, equipment, and associated work practices employed by electric utilities. These systems often operate at higher voltages and involve different grounding philosophies compared to the premises wiring systems covered by the NEC. For instance, many utility systems rely on effectively grounded systems where the neutral point of the supply transformer is intentionally connected to earth. This connection provides a low impedance ground fault path and in some cases may mitigate the need for a separate equipment grounding conductor. Furthermore, the NESC recognizes that certain equipment and installations within the scope of electric power systems may have inherent grounding characteristics or utilize alternative grounding methods that achieve an equivalent level of safety. For example, equipment directly bonded to a metallic structure that is itself effectively grounded may not require a dedicated EGC. It is important to emphasize that the absence of a universal EGC requirement in the NESC does not imply a disregard for safety. Rather, it reflects a nuanced approach that considers the specific characteristics and grounding practices prevalent in electric power systems. The NESC mandates adherence to other grounding principles and practices aimed at ensuring safety. These include proper bonding of metallic enclosures, grounding of conductive parts that are likely to become energized, and the establishment of a low-impedance ground fault path to facilitate the operation of overcurrent protective devices. Moreover, the exception for coal mines highlights the NESC's recognition of specific environments where the presence of an EGC is deemed essential for safety. Coal mines present unique hazards such as the risk of explosions due to the presence of methane gas and coal dust. An EGC provides a critical safety measure by minimizing the potential for spark ignition caused by ground faults. In summary, the NESC stance on the EGC requirements is based on a comprehensive assessment of the safety considerations specific to electric power systems. While an EGC is not universally mandated, the NESC incorporates alternative grounding practices and addresses specific environments like coal mines where an EGC is deemed necessary. To ensure compliance with the NESC and to guarantee the safe operation of electrical systems, it is crucial to consult the specific requirements outlined in the latest edition of the code and to seek guidance from qualified electrical professionals. Understanding the NESC's perspective on EGC requires a deeper look into grounding principles, fault current paths, and the specific context of electric power systems. Firstly, grounding serves two primary purposes in electrical systems. The first is system grounding, which involves intentionally connecting a conductor, usually the neutral, to the earth. This establishes a reference point and helps stabilize voltage during normal operation. The second is equipment grounding, which involves connecting non-current carrying metallic parts of equipment to ground. This is to provide a low impedance path for fault current. Secondly, fault current flows through the equipment grounding conductor back to the source. This high current causes the overcurrent protective device, such as a circuit breaker or fuse, to trip quickly, de-energizing the circuit. Without an effective equipment grounding path, fault current could flow through unintended paths such as a person touching the equipment, leading to electric shock. Thirdly, the NESC covers electric supply and communication lines, equipment, and associated work practices employed by electric utilities. These systems often operate at higher voltages and involve different grounding philosophies compared to the premises wiring systems covered by the NEC. The NEC applies to premises wiring systems, such as those found in homes and businesses. NEC Section 250.4. A5 discusses grounding electrical equipment and ensures that the electrical equipment is grounded in a manner that creates a low-impedance circuit facilitating the operation of the overcurrent devices. The NEC also contains tables such as 250.122, which provides the minimum size of equipment grounding conductors for grounding raceway and equipment. The NESC, on the other hand, allows for more flexibility in grounding methods, recognizing that some equipment may be inherently grounded or utilize alternative grounding methods. Fourthly, the NESC addresses scenarios where equipment is directly bonded to a metallic structure that is itself effectively grounded. In such cases, a separate equipment grounding conductor may not be required, as the metallic structure provides an adequate ground fault path. However, it is important to ensure that the metallic structure is indeed effectively grounded and that the connection between the equipment and the structure is robust and reliable. Fifthly, the exception for coal mines highlights the NESC's recognition of specific environments where the presence of an EGC is deemed essential for safety. Coal mines present unique hazards, such as the risk of explosions due to the presence of methane gas and coal dust. An EGC provides a critical safety measure by minimizing the potential for spark ignition caused by ground faults. The equipment grounding conductor helps to quickly clear the fault, reducing the risk of an explosion. Sixthly, it is important to note that even in situations where the NESC does not explicitly require an EGC, it still mandates adherence to other grounding principles and practices aimed at ensuring safety. These include proper bonding of metallic enclosures, grounding of conductive parts that are likely to become energized, and the establishment of a low-impedance ground fault path to facilitate the operation of overcurrent protective devices. Bonding involves connecting metallic parts together to create an electrically conductive path. This helps to equalize the potential between different metallic parts, reducing the risk of electric shock. Seventhly, consider a scenario where a metal enclosure houses electrical equipment. According to the NESC, this enclosure must be bonded to ground. This can be achieved by connecting the enclosure to the grounded neutral conductor or to a dedicated grounding electrode. The purpose of this bonding is to ensure that the enclosure is at the same potential as ground, preventing it from becoming energized in the event of a fault. Eighthly, grounding electrodes play a crucial role in providing a low-impedance connection to earth. The NESC specifies requirements for grounding electrodes, including their type, size, and installation. Common types of grounding electrodes include ground rods, ground plates, and underground metallic water pipes. The selection of the appropriate grounding electrode depends on factors such as soil resistivity and the availability of suitable grounding mediums. Ninthly, overcurrent protective devices are designed to automatically interrupt the flow of current in the event of an overload or short circuit. These devices, such as circuit breakers and fuses, are essential for protecting electrical equipment and preventing fires. The NESC requires that overcurrent protective devices be properly sized and installed to ensure that they operate effectively in the event of a fault. Tenthly, consider the implications of using an undersized equipment grounding conductor. If the EGC is too small, it may not be able to carry the fault current effectively. This can result in a slow clearing of the fault, increasing the duration of dangerous touch potentials and potentially damaging equipment. Therefore, it is crucial to select an EGC that is appropriately sized for the application. 11thly, the NESC recognizes that certain types of equipment may have inherent grounding characteristics. For example, a metal pole supporting an overhead power line may be inherently grounded due to its contact with the earth. In such cases, a separate equipment grounding conductor may not be required, provided that the pole is adequately grounded. 12thly, the NESC acknowledges that alternative grounding methods may be used in certain situations. For example, a high-resistance grounding system may be used to limit the magnitude of ground fault current. This type of system can be beneficial in reducing the risk of arc flash and equipment damage. However, It is important to carefully evaluate the suitability of alternative grounding methods and to ensure that they meet the requirements of the NESC. 13thly, the NESC provides specific requirements for grounding portable equipment. Portable equipment is more susceptible to damage and misuse than permanently installed equipment. Therefore, it is important to take extra precautions to ensure that portable equipment is properly grounded. The NESC may require the use of a flexible cord with an equipment grounding conductor for portable equipment. 14thly, the NESC addresses the grounding of electrical equipment in hazardous locations. Hazardous locations are areas where there is a risk of explosion or fire due to the presence of flammable gases, vapors, or dusts. The NESC requires that electrical equipment in hazardous locations be specifically designed and installed to prevent ignition of these flammable substances. Grounding plays a critical role in minimizing the risk of ignition. 15thly, consider the challenges of grounding electrical equipment in remote locations. Remote locations may not have access to a reliable grounding electrode system. In such cases, it may be necessary to install a dedicated grounding electrode system. The NESC provides guidance on the design and installation of grounding electrode systems in remote locations. 16thly, the NESC addresses the grounding of electrical equipment on structures such as buildings and bridges. These structures may have their own grounding systems. It is important to ensure that the grounding systems of the electrical equipment and the structure are properly interconnected to create a common grounding system. 17thly, the NESC provides requirements for the grounding of communication equipment. Communication equipment often operates at low voltages and may be susceptible to damage from voltage surges. Grounding helps to protect communication equipment from damage. 18thly, the NESC addresses the grounding of electrical equipment in underground installations. Underground installations are subject to unique environmental conditions such as moisture and corrosion. It is important to select grounding materials and methods that are suitable for these conditions. 19thly, the NESC provides guidance on the inspection and testing of grounding systems. Regular inspection and testing of grounding systems are essential for ensuring that they are functioning properly. The NESC specifies the procedures for inspecting and testing grounding systems. 20thly, consider the importance of documentation for grounding systems. Proper documentation of grounding systems is essential for facilitating maintenance and troubleshooting. The NESC recommends that grounding systems be documented in detail, including the location of grounding electrodes, the size and type of grounding conductors, and the results of grounding tests. It's important to remember that the NESC is a complex document and requires careful study and interpretation. Consulting with qualified electrical professionals is highly recommended to ensure compliance and to maintain a safe electrical environment.